Can you hear me?
Yes, ma'am.
Yes, ma'am.
So once you decide the clearance, so this is the available height for your lower winding. So available height, and this is the individual, that composite conductor. So once you know the height, you know how many turns you can accommodate in one layer. Now for helical and helical and spiral, the main difference is that for helical we give a intentional one turn twist. So if the number of turn in one layer is n, then the height will be n plus 1 into height of the individual composite conductor. So this is the height of the winding. So this one we know from HW minus twice HY. So this also we know. So from here we determine a value of n. Now that is n turns per layer. Now this should be, obviously should be an integer. We cannot have a fraction. So what we know, we have determined the number of turns at the beginning, LV winding. So on one limb, we will have that half of it on the one limb divided by this n determined here. So this will be number of layer. Again, this should be rounded off to a integer, because number of layers should be an integer. So turns per layer will be, n modified will be number of turns per limb divided by 2 here, because I have assumed number of layers equal to 2. It will be divided by number of layers. So accordingly, what you will modify your winding height. Winding height will be n modified plus 1 into a height of the conductor. Now, obviously, accordingly, your window height get modified, because clearance is fixed depending on the voltage. So this plus twice the clearance will be your new window height. Now next we go for the high voltage winding. For the high voltage, we find out the current in the same way from the kVA and the high voltage rating, and the what will be the type of the winding is same. Also the conditions are same. So if you have a low voltage on both sides, lower than 11 kV, then you will have helical on both sides. So if it is a helical winding, it will be done in the similar way as we have done for the low voltage side. Now, first of all, we have to decide the high voltage turns. High voltage turn will be high voltage voltage by low voltage voltage. That is the voltage ratio defined in the problem into low voltage number of turns into I have increased by 5%. That is because I have defined a tapping. That maximum was plus minus 5%. Unless you provide that extra 5% turn, it will not be provided. We cannot provide that 5% tapping. So that number of turns should be provided. So it is the number of HV number of turns. So again, this quantity has to be a multiple of 2, because this multiple of 2 is coming because it is a single phase transformer. When you go for 3 phase, that is, it is on the same limb, that is not required. For the helical winding, the design should be as the same way. Now the other two I will define. The first one is the crossover winding. If the current is small, defined as I have defined, it is less than 45 ampere, then we will go for crossover. Crossover is used with circular conductor. Circular conductor, this is green one is insulation. This is the first layer, this is the interlayer insulation what we have. Now this is the LV winding on which we will have the HV winding. Now if it is a crossover, it is divided into sections. Each section is called a stack, and each stack for crossover typically will have 1500 volt. So from that we decide how many number of stacks we will have. Now first we will have the conductor area. It is the current divided by current density. So this will be equal to pi by 4 d square, where d is equal to root over this is the bare diameter of the conductor. So again, similarly, we have the SWG wire gauge. That also table is, I have given the table, but it is that chapter 7, that is a large file. In that you will get that table 7.5. I cannot separate here, so I have sent the whole file. From there you will take the nearest, we can see here. Anyway, it is not open here, so this is the table 17.8. So diameter, say you have calculated diameter of 4.5, then you can go for this one. Your current density will be slightly more, this is slightly less. Because if you select this one, current density will be too low. Similarly, we have to go for the nearest one. This is the bare diameter. Then with on which we will have 0.25 insulation. So now here also we have to decide how now on the number of stacks per limb will be high voltage divided by 1500 divided by 2, because your total number of stacks will be high voltage divided by 1500, and that divided by 2 will be stacks on one limb. Now say in the figure I have shown 4 stacks. Now the 4 stacks, the gap between stacks minimum is 6 millimeter, and one gap I have shown as 10 millimeter. This is provided larger because in the middle to bring out the tappings. To bring out the tappings, one will have larger gap. So what is the height? You can see if say n is the number of conductors per layer height wise. So n into number of stacks plus 6 into, if you have n number of stacks, you will have n minus 1 number of gaps. One is 10 and the other n minus 2 gaps will have 6 millimeter. So your height of each stack will be height of winding height, LV winding height minus 10 minus n1 minus 2 into 6 divided by n1. Then it is the height of stack, each stack. If it is height of each stack, then turn per stack will be that this is the number of turn divided by 2. It is number of turns per limb divided by, this is n1, that is number of stacks. So this is the turns per stack. Number of conductor arranged in one layer per stack. We have the heights per stack and we have the diameter d plus insulated. This is the insulated diameter. So if you divide, you will have number of conductor per layer for a particular stack. If that is the number of layer will be, this is the n stack, this is the turns per stack divided by turns per layer per stack. It should give the radial layer, that is, this is the turns per layer per stack into radial layer will be the total number of turns per stack. So this radial layer should be an odd integer. That is why Why? Because we wouldn't like this. We start from here, we finish here, then insulation, and we start from here, finish here, then we again start from here, finish here, start from here, finish here, and this is a odd layer I have shown. So if you start, this is finish, start, finish, start, finish, start, finish, start, finish. So you will finish here. If you finish here, you will connect with the next start here, and you will go on like this. If we have even layer, then you will finish here. So you have to connect like this. So avoid that cumbersome connection. You should have odd number of stacks, the odd number of layers. So number of layer. Now again, when you have to make it odd, that you have changing the value what you have get earlier. So automatically you will have number of layer modified equal to n stack by number of layer what we have decided now. So modified, that will modify the stack height because this one we have modified into this one is fixed. So stack height will modify. So that will decide on the high voltage winding height. Actual high voltage winding height will be this number of H stack modified into N1 plus 10 plus N1 minus 2 into 6. In the previous equation, just now we have this is the same equation here. So this high voltage height and low voltage height should be approximately equal. It cannot be exactly equal, should be approximately equal. Now inside this 10-15 millimeter difference is considered to be okay. So okay, you have to decide on. Now we have to, next is if we have a higher current, then we go for disc winding. Now disc winding is used with rectangular conductors. So conductors are selected as I have described in case of helical winding. So how it is arranged? It is arranged like this. Each and every one is a single disc. That is, disc is a concentric. This is a disc type of winding is wouldn't like this. It is a continuous disc winding. So inner first one will start from inside. So inside, outside. It will start from here and end here. Second one will be in the reverse. It will start from here and it will end inner side. So then it will end here. The next one will start from here and end here. This way the conductor is continuous. So it will go on like this. There is a gap between two successive discs. It's a 6 millimeter. Now disc has a possible best ventilation because conductor is in contact with the oil. And all the conductors are individually connected with the oil. So it is used for high voltage, high current transformers. So from here, you can see that if this is the HHV or the conductor height. So your number of discs will be height of the winding available minus 10 minus n disc minus 2 in the same way, the same logic. That is, individual is 6. If you have n disc, the number of gap is n minus 1, 1 is 10. So n minus 2 gaps of 6 millimeter, 1 is 10 millimeter. This is the height available divided by HHV will be the number of discs. So this should be an integer. So turns per disc will be n disc will be turns per limb divided by n disc. So all this should be made integer. We ultimately calculate the high voltage is equal to HHV into n disc plus 10 into n disc minus 2 into 6. Then in the reactance calculation also is an empirical relationship. Now, what I have shown here is helical winding for both low voltage and high voltage. Low voltage, I have shown 2 layers. In high voltage, I have shown actually 4 layers, 2 and 2 clubbed together. So, but the formulas are applicable for others also. If people who have crossover or disc winding, instead of 2 sections in the high voltage, you will have only 1 section that is up to this. These other 2 will not have. So I have defined certain dimension for crossover and disc. You will have up to D6 you will have, not D7 or D8. So D is the core circle diameter, A1 width of first layer of LV, in this case single layer, so this is WLV. A2 width of second layer, it is WLV. A3 width of first section of HV. Here I have considered 2 layers clubbed together. So WHV and 0.5 is interlayer insulation. Similarly, A4. So C0 is the clearance between core and LV winding. Approximate value is this. C1 clearance between HV and LV winding. This is the approximate value. Whatever comes, you round it off to nearest integer. So C2 is the clearance between HV winding of 2 limbs. This is a few millimeter more than C1. B1, B2 are oil duct between layers. This is standard 10 millimeter. So we can calculate the diameters individual, that is D1 will be D plus twice C0. D2 will be D1 plus twice A1. D3 will be D2 plus twice B1. D4 will be D3 plus twice A2 and so on. So we have all the dimensions. So reactance factors are defined as LV reactance factor, that is for the first section of LV winding, that is pi D1 plus D2 by 2 into A1 by 3. A1 is the width of the section into 1 by HLV. So LV duct factor is pi into D2 plus D3 by 2 into B1 by 4 into 1 by HLV. Namely, this is the reactance factor for second layer of LV. This is for the middle duct between LV and HV. This is for first section of HV. This is duct between 2 sections of HV, and this is for second section of HV. Now, if you have crossover or disc winding, then these 2 are not there. Up to this you will have, because your D7 and D8 is not there. Up to this only you will have. So your total reactance factor is summation of all this. Your leakage reactance will be, now actually we have half of the turns on one limb. So you have calculating for one limb. So twice pi F mu 0, half of the turn square into total reactance factor in 10 to the power minus 3, as they are connected in series, into 2. This is for the single phase transformer arranged in 2 limbs. So this is your X1. So percentage reactance will be XLV into X1 into by WLV into 100. This is epsilon X. Now whether you use low voltage, high voltage, that is immaterial. The percentage will come same. So this is percentage reactance. Then we can calculate the percentage resistance, inner diameter of LV, outer diameter of LV. So mean diameter is D1 plus D4 by 2. Length of mean turn is to pi into D mean. The conductor cross section is number of parallel conductor into individual conductor. if it is a circular conduct, for LV it is rectangular, so no resistance will be, this is the resistivity into length of mean turn into number of turns divided by the total conductor area. I have considered 0.021. This is resistivity of copper at 75 degrees centigrade. So this is a hot resistance. Similarly, we can calculate for the high voltage. So then calculate the total copper loss. ILV square RLV plus IHV square RHV. It is increased by 10% to take into the stray loss. So this is the total copper loss. Copper loss divided by the kVA into 100 will give you the percentage resistance. It should be within 1%. So from here we can calculate the percentage impedance that should be within the 10% of the value given in the problem. That is, here we have specified the percentage impedance in the problem. Now from here we have up to this, you calculate for a value, then you can see that your percentage impedance is not matching. Then what to do? Then we have to, because the dimensions has to be changed. You understand one thing, because percentage, if you see the reactance factors, reactance factor expressions, you can see that if diameters increases and the height decreases, then reactance factor will increase. Now say your percentage impedance is less than the value given. That means your percentage impedance is small, then decrease the height of the winding. That automatically will increase the diameter. Decrease the height means, that is, if you have a single layer helical, go for the double layer. That will automatically decrease the height and increase the diameter, and this reactance factors will increase. That will increase your impedance. And if it is more, it comes more, then you go reverse. That is, the height should be increased and automatically will reduce the diameter, and the impedance should, and that is that way we match the impedance within that. The limit I have given is 10% of the given value. Okay. Now, normally what I specify for in other years, that is, I ask them to perform three iteration for 3 different values of K. Then you can see that the copper and the iron weight are changing, copper cost and iron cost are changing. This year we started late, so I won't ask you to do 3, but I will ask you to complete it for 1 value of K, so that you match the, but the percentage you should, the impedance you should match within 10%. You can start with a value of 0.5, because I have not specified distribution or power and are given arbitrary ratings. So start with a value of 0.5 and you can calculate the results. Then after that, we have to calculate the weight of the copper and other things that we can discuss. Up to this, you can start calculating and you can contact me if you have any difficulty. We can sit after say for 2 weeks that to see how much progress you can make. Now I normally go to the university on Monday, Wednesday, Friday. So if you want, you can come and show me. Okay, I'll stop here today. So you can start calculating. Hello? Once you start, you might face some problems. You can always contact me on phone or on WhatsApp to understand. Okay.
Yes, ma'am.